Hello friends, let's get back to the second module of practical aspects of control design. Okay, so practical aspects of control design. All right, so this is the second module of the main module, which talks about practical aspects of control design. Okay, so we would discuss in detail what are the discontinuous control modes. Okay, and these discontinuous control modes are the first three control modes of the whole set of control modes here. Okay, so these are the first three are the discontinuous control modes. All right, and these are the continuous control modes. Okay, control modes. So these I can write it as control modes. All right. So the first three are the discontinuous control modes. We will deal with them one by one, and then we'll get into this continuous control mode, starting from P controller, I, and the composite controllers, which are PI, PD, and PID. Okay. So the first discontinuous control mode is a two-position control mode. And obviously, from the definition of this control mode, you can see here that first, as I told you, that error is generally calculated as reference minus the actual value. Okay, actual value. Okay, so this is the way we calculate the error. Okay, so if the error is less than 0, that means error is less than 0 means that the actual value is greater than the reference. Okay, if error is greater than 0, it is converse. That means that the reference is greater than the actual value. Okay, so what do you do in such cases is what we need to understand here. Okay, so that means if error is less than 0, then you switch the controller to 0%. If the error is greater than 0, then you are switching the controller to 100%. Okay, fine. So this is the way you are operating the controller. Okay, so if you operate the controller in this way, wherein you have just two positions for the control output represented as P. Okay, so let's say the controller output is represented as P. In some textbooks, you are given the controller output as U as well. Okay, so for example, here in this textbook, which we are referring to, the controller output is represented by P. So what you can see clearly here is if the error is less than 0, control output is 0%. If error is greater than 0, it is 100%. Okay, so is it possible that the controller with such a philosophy works practically in real time or not, is what we need to very clearly understand. Okay, so let's try to see here. So first we'll take a quick example, and then we'll go to a numerical example to understand this concept much more clearly. Okay, so first let's try to understand a very common example which we encounter in our daily lives, which is a water heater. Okay, so what we do with the water heater, most of our bathrooms have this water heater. So what we generally do is we switch on the power supply. Okay, switch on the power supply to the heater, right? To the heater, and just leave it, right? So what generally happens is we switch on the power supply and leave the heater on. After some time, you can see that the indicator on the water heater gets off. That actually means that even though you have switched on the power supply to the heater is not accepting any electrical power. Okay, that actually means that the power supply is cut off. Okay, power supply is cut off. All right, and then after some time, you would see that once you start using hot water, after some time the cold water enters the heater again, and then you will see that the heater automatically turns on. Okay, So these two things happen automatically. Okay, these two things happen automatically. That actually means that if the water is getting heated too much, then the power supply is cut off, and if the water is getting colder, then the power supply is turned on again to the heater. Okay, so this is the way actually a heater works. All right. So now that this is the kind of operation which we are expecting from a heater, is there any problem with this approach is what we need to understand. Okay, so there is a problem with this approach, because if, for example, say let's say the error is reference minus actual value. Okay, this is the expression to calculate the error. Okay, now let's say we are looking at error is the reference temperature minus the actual temperature. All right, so actual temperature is the temperature of the water, reference is that of the set point of the heater. Okay, so let's say for example the set point P reference is equal to some 85 degrees Celsius. Okay, we are not keeping it at the boiling temperature anyway, which is 100. We keep it much little below that. Now it comes to around 85 degrees, for example. All right, and let's say the actual temperature is, say for example, 82 degrees Celsius. That actually means that the heater should be switched on, and once it crosses 85, heater should be turned off. Okay, similarly now if the temperature is reaching 86 degrees, okay, it should be switched off, right? That's the thing which we need to understand. Okay, so let's just take these two considerations. Okay, so let me just draw a plot of error versus time. Okay, error versus time. So assume that now we are just solely relying on this expression of error, which is the reference minus the actual value, which could possibly change dynamically over time. Why? Because since we are trying to feed in water as we use water downstream, the hot water, once we use it downstream, the cold water enters the heater. Okay, so therefore the temperature goes up and down because of heating and the cooling effect of the incoming and the outgoing flow. Okay, so therefore the error would slightly go up and down like this. Okay, so instantaneously you can see that the error would oscillate up and down around the zero value, okay. So but then here in this expression, if you see, we have just taken this condition that error is less than 0, we should do something, error is greater than 0, we should do something. That means if error is less than 0, we should possibly switch off the heater, which means that it is equivalent to 0%. If error is greater than 0, you switch on the heater, which is 100%. Okay, so this is the way to understand. Now, is it possible that such kind of logic would work? From this analogy, what I told you here, that it is not possible, because the error keeps fluctuating around 0, and therefore your heater would turn on and off continuously, and therefore it would damage the control circuit of the heater. Okay, so therefore it is not desirable. Okay, that actually means that we should avoid switching of the heater when the error is hanging around this value of 0. That means if I keep a certain band here, okay, if I keep a certain band here in which the heater would not really turn on or off, in such a case I could protect the heater from damage. Okay, so therefore what would I do is I would suggest a band here, and that band would help the heater to turn on and off with a certain sensitivity. Okay, so if the band is larger, the sensitivity will be larger. That means, and if the band is smaller, then the sensitivity will be smaller. Okay, so let's try to understand that here with the same example of the situation here. So for example, you are looking at a situation wherein you have the reference to be 85 degrees Celsius, and then you are looking at the heater. If, for example, the actual value of the water inside the heater is, for example, 88 degrees Okay, that means E is equal to reference minus actual. Reference is 85 minus actual is, let's say, 88. Okay, that means you have minus 3 degrees Celsius of error. Okay, so let's say I keep this to be 88 degrees Celsius here, and on the right hand side let me keep this as 82 degrees. Okay, let's try to understand this way. Okay, so plus delta EP, I have added plus 3 degrees, and this is minus 3 degrees, or the other way around here. Okay, so this is plus 3 degrees and minus 3 degrees Celsius here. Okay, so with this we can understand the principle of something called the neutral zone here. Okay, so the band which I was talking about previously, okay, the band which I was just talking about can be understood with this example. Okay, this neutral zone. Okay, so what we have here is, for example, you assume a situation wherein you have a heater with this neutral zone. Okay, so as we go along, you will understand what is actually a neutral zone. Okay, so instead of when the error is going up and down around zero value, okay, when the error is going up and down around zero value, this is the time and this is the error. All right, then this is the band which I am talking about, and this band is the neutral zone. Okay, this band is the neutral zone. Let me just put this here, neutral zone. All right, so this band would be called as a neutral zone. What exactly the neutral zone does to this the whole control philosophy here is that, so what do you think should happen here? Now, for example, you have a reference of 85 degrees Celsius. Okay, let's say you wanted to have your water heated at 85 degrees Celsius. Okay, and you see that, okay, let's say for example you started at 85, and after some time the water gets cooled down to 82. Okay, 82. Okay, and it is further going below 82. Okay, when it is going further below 82, so what you do is you try to switch on the controller. Okay, that means you are extending power to the heater. Okay, so the path followed is like this. The way I am showing here is that you follow the path this way. That means you are switching on the heater. Okay, now once you switch on the heater, as I told you that you are having this kind of neutral zone here. The neutral zone is reflected in terms of the error zone here. So how much is the neutral zone here? Let's say I have assumed here minus 3 degrees to plus 3 degrees. So 6 degrees Celsius is the neutral zone here. So in this 6 degrees, okay, that means you start with an error of minus 3 degrees to an error of plus 3 degrees. You do not take any control action. That means that this zone, you are not doing any control action. You are not performing any control action. That means your output will still remain at 100%. All right. So initially, when the temperature is dropping below 82 degrees, that means the difference is going more than minus 3 degrees. So you are switching on the heater. Now, in order to switch off the heater, what you do is you would wait until the temperature increases up to 88, for example. Okay. You can always choose this 88 depending on the safety conditions of your heater. I am just putting some value here. Okay. I am just putting some value here. All right. And then, so what happens actually is, that means beyond 82, that means below 82, that the heater is switching on. Above 88, the path followed will be like this. Below 82 degrees Celsius, above 88 degrees Celsius is what you would see the neutral zone to work here. All right. So this is a very classical and very, very simple example of a two-position control system. Okay, two-position mode or a two-position control system where you have just working on the control output to be 0% or 100% based on the error, which is either greater than 0 or less than 0. Okay. I hope you understood the practical difficulties in implementing the system and how the neutral zone plays a role here. Alright. So this is one very good example to understand. Okay. Next, we'll try to see a numerical example where we try to understand a control system in which you have a temperature control system corresponding to that of water. Okay, temperature of water is being controlled, okay, by a two-position controller, and of course there is a heater. Very similar situation to what I have taken before. Okay, so that means you are having a tank which has a heater, and then you are controlling the temperature of water in the heater. So what are the conditions here? One, the important conditions here given are when the heater is off, alright, the temperature drops at a rate of 2K per minute, and when the heater is on, the temperature rises at 4K per minute. And the set point you are taking it as 323, okay, and the neutral zone is plus or minus 4% of the set point. That means 323 plus or minus 0.0, it should be written as 0.04 into 323, okay. This would give you the value of the neutral zones, okay. Now, one more thing is that there is a 0.5 minute lag at both on and off switch points, okay, that is quite possible, okay, in a practical system. And what is the question asked? Now, you are asked the question, right? What is the period of oscillation, and how do we plot it, okay? So, let's try to first understand the whole thing properly. Now, let's say you are starting at some set point value, you are given 323 Kelvin, alright, okay. Let's try to understand this with the help of the diagram in the next page. We've already solved examples. I just wanted to give you quite a bit of intuition on how does this system work, okay. So that means here is a set point, okay, you are calling this set point to be 323 Kelvin, okay. And the neutral zone, as I told you, is plus or minus 4% of 323. That means you have plus or minus 12.92 Kelvin, which added to the set point gives you, this comes up to 335 Kelvin, and this goes up to 311 Kelvin, okay. So it comes up to 311 Kelvin and there is 335 Kelvin, okay. So between these two temperature ranges, you will have the on-off control, okay. And this is called the neutral zone, okay. This is called the neutral zone, okay. So that means, for example, if you are starting at point number 1 and you are trying to reach point number 2, and this is 3, let me just mark these points, and this is 4, alright. And we need to find the period of oscillation. That means you started at a point 1, and then let me just, possibly this should be 4 and this should be 5, okay. That means you want to find the period of oscillation. That means this is the time period you want to find out, okay. This is the time period you need to find out, okay. So for that, you can directly try to solve this problem like this. So for example, you start at 323 Kelvin, okay. If you are starting at 323 Kelvin, which is at the set point, and this, that means this controller is not even on here, okay, not even on here. That means that the water level, water temperature would go down, okay. So up to what point should it go down is the question now, okay. To what point should it go down? It should go up to 311 Kelvin, because it specifies the lower band or the lower neutral zone, okay, lower point in the neutral zone, okay. So you have 335 Kelvin and 311 Kelvin as the neutral zone, okay. So these are the 2 points you need to understand, 2 limits you can see, okay, upper limit and the lower limit, okay. So that means if you are at 323, you need to come down. That means controller is off, you need to come down. So you need to reach 311 Kelvin, okay. That is one point. Second point is you always have a lag of 0.5 minutes here. Okay, that means that even though you detect 311 Kelvin, you will not be able to stop. You need to wait for another 0.5 minute to stop. Okay, that means the controller would only stop after 0.5 minute lag. All right. So now, what is the effect of this 0.5 minutes on this control system is as follows. So now, when I want to come down, okay, from 323 to 311, and the coming down means that the drop in temperature, right? Let me just come back here. Drop in temperature is 2 Kelvin per minute. Okay, that actually means that 323 is the upper limit and 311 Kelvin is the lower limit, and divided by 2 Kelvin per minute will give you the time. All right, will give you the time. Okay, so whatever time you get here, time, okay, you need to add 0.5 minutes to it, because after that you are going to revert back to the control action. Okay, so that means whatever time you get here, depending on that time you add 0.5 minutes, you are going to go ahead. Okay, but then you need to add the practical condition here. What is the condition here? Is that you are at 311 Kelvin, and after a delay of 0.5 minutes, what will happen is, if the delay is 0.5 minute and your rate at which the temperature is decreasing is 2K per minute, so you have 2K per minute. In 0.5 minutes, you will reduce your temperature by 1 Kelvin. That means here you will have 310 Kelvin. Okay, so that means the lower limit after the delay, that means at 0.2 is 310 Kelvin. All right, 310 Kelvin. Okay, now similarly we need to find the upper point, which is 3 now. Okay, so to reach the upper point, the goal is to reach 335. Okay, that means from 310 Kelvin to 335 Kelvin. Okay, now this is the situation wherein the heater is turned on. So you are increasing your temperature at a rate of 4K per minute. Okay, that means this is 15 by 4 minutes. Okay, and of course there will be a delay of 0.5 minutes for sure. Okay, 0.5 minutes for sure. Okay, so that means you would reach 335. In addition to that, since there is a delay of 0.5 minutes, in 0.5 minutes the rate of increase would be 2K. That means you would reach 337 Kelvin. You would reach 337 Kelvin. Okay, so that means this point would be 337 Kelvin. This point 3 would be 337 Kelvin. All right. Now from 337 to, this calculation is a little easier based on the rate, because we are not really handling the controller right now. This is a part of the cycle. So from 337 337 Kelvin to the set value. What is the set value? 323 Kelvin. 323 Kelvin. What is the time it's going to take? It is going to decrease, right? So 323, you take this difference. What does this difference give you? Is 14 Kelvin. Okay, and the rate is 2K per minute. Okay, so it actually means that it will take how many minutes? Around 7 minutes. Okay, so 14 divided by 2 Kelvin per minute is the rate of decrease. So we'll get around 7 minutes here. Okay, so now you need to add all the times here, and here. Okay, so if you add these up, then you would get this time period to be around 21.75 minutes. Okay, that means you start with a set point, the actual value in the neutral zone, and then coming back to the same point after certain time. Okay, that time period is equivalent to 21.75 minutes. Okay, this is one simple way to calculate the oscillations, okay, the time period of oscillations of the system. Okay, I hope you understood this example. Okay, thank you.